In this section, we'll be looking at the reverse process of differentiation known as anti-differentiation. Quite the blunt name. So essentially, we'll be looking at if we're given a function, if we're given a function that we know is a derivative, determining what the original function was, what we call the antiderivative. So let's take a look here and put in more concrete terms because that sounded a little bit esoteric. Whereas first semester has looked at finding the derivative f prime of a function f, we will now start looking at the flip side of this. Provide a function f, what is the antiderivative capital F of the function? We'll call it capital F or big F for notational purposes. To represent when we are determining an antiderivative, we will use the following notation known as an indefinite integral. So what this says right here is that the antiderivative of a function lowercase f is going to be equal to uppercase f, okay? So the integral sign is used except for upper and lower bounds. This connection will be explored further in 4.4a and 4.4b. So if we take a look at the following functions right here, big G of x is equal to x squared plus 4. Big G of x equals x squared plus 1. Yeah, I'm not going to count that many zeros. And big G of x equals x squared plus pi. What we'll notice is that if we take the derivative of all of these functions right here, we're all going to get the same exact derivative, 2x. So there's always a possibility that there could be a constant added on to the antiderivative, okay? To account for this possibility, all antiderivatives will have a general constant c added on. Unless we have further information, we cannot determine what c is. In the above example, for example, we would write that big G of x, our antiderivative, is x squared plus c because we cannot determine what this constant is, whether it's pi, whether it's 1 followed by a bunch of zeros, or whether it's 4, okay? To illustrate this, all right, if we're looking at 2x, okay, which again is what we calculate our derivative to be, if we're looking at 2x and we're trying to determine what the antiderivative is, we could say that is x squared. But again, because we don't know what the constant is and the derivative of constant is 0, we have to add a plus c here until we have further information in order to determine what c is. And in the words of SpongeBob, you always need this plus c when you're calculating antiderivatives. We can never forget it, okay? So properties of antiderivatives, okay? If a function lowercase f has an antiderivative big F and g of x has an antiderivative big G, then the following holds for our functions, all right? So the constant multiple rule, if we have k times lowercase f of x, then the antiderivative is going to be k times uppercase f of x. And then we have the sum of difference of functions. If we have f of x plus or minus g of x, then the antiderivative is going to be uppercase f plus or minus lowercase g. Okay? Please note that there are no product or quotient rules for antiderivatives. So even though we have product and quotient rules for derivatives, there are no such rules for antiderivatives. And then lastly, we have the power rule for antiderivatives, okay? So if x to the n is our function that we're interested in finding the antiderivative of, the antiderivative of x to the n is going to be 1 over n plus 1 times x to the n plus 1 plus c. And we can check this real quick because if we take the derivative of x to the n plus 1 right here, that's going to give us n plus 1 times x to the n power. The n plus 1s are going to cancel out and leave you with just x to the n. And then of course we have the plus c right here because when we take the derivative of plus c, we're going to get 0. Please note that n cannot equal negative 1 for this rule to apply, all right? Because in the case that n equals negative 1, we're going to have x to negative 1 power, which is equal to 1 over x, the indefinite integral of 1 over x. And if we think about this a little bit, run the process of differentiation in reverse, we know that the function that gives us a derivative of 1 over x is the natural logarithm of x. So the antiderivative of 1 over x is going to be the natural logarithm of x plus c. Again, as we can confirm by taking the derivative of a natural logarithm of x plus c. So let's look at some examples of antidifferentiation. So evaluate the indefinite integral of 12 times x cubed plus 2 times x to negative 1 power. So what we're going to do first is we're going to rewrite this x to the negative 1 power as 1 over x right here, and there should be a 2 here, but I forgot to include the 2 in my solution. Okay. So what we're going to do is we're going to apply the properties for definite integrals. So we notice we have indefinite integrals. We notice we have a sum of functions right here, so we can break up the integrals. The integral of 12x cubed plus the integral of 1 over x dx. Again, forgetting that 2 that I have right there. Okay. Next, we notice we have a constant multiple attached to x cubed, so we can factor it out. So that becomes 12 definite integral of x cubed plus definite integral of indefinite integral of 1 over x. So now if we apply the power rule to x cubed, okay, we're going to get x to the 4th over 4. And then if we evaluate the indefinite integral of 1 over x, we're going to get the natural logarithm of x. And then lastly, we have the plus c attached. And then in the last step, we can simplify this x to the 4th over 4 that multiplies to 12, which comes out to give us 12 divided by 4, gives us 3 times x to the 4th, plus natural logarithm of x, plus c. Thus, this gives us the indefinite integral for our specific function here.